Hello, chemistry students. Today we are going to talk about subatomic particles. So, particles that are smaller than an atom. By the end of this lesson, you should be able to calculate the number of protons, neutrons, and electrons for any atom. Okay, so let's start by thinking about a pure element. The one I've chosen to talk about today is gold. Very early scientists, when they started thinking about atoms, they started thinking, what would happen if I cut this gold coin in half? And then cut it in half again, and again, and again, and again. How many times can I cut this piece of gold in half before I can't cut it in half anymore? So that's where the term atom actually comes from. It means an indivisible piece of matter. Okay? So the idea of the atom actually began as a philosophic thought, not a scientific experiment. The first philosopher that we know about that started thinking about the atom was Democritus. He was a Greek philosopher born in 1460 BC, and he reasoned that atoms were indivisible and indestructible. So his ideas were based off of observations of matter, and they did not use the scientific method whatsoever. John Dalton was able to build off of Democritus's idea and actually prove it to be true in 1700s. He was an English chemist and school teacher. He used experimental methods to look into Democritus's idea of the atom. Specifically, the experimental method he used was mass. It was around this time period that the idea of mass was very popular, and that's what he used to prove Democritus right. The result of Dalton's work was his atomic theory, which had 3 parts. And I would like you to write his atomic theory down because to this day it is mostly correct. The first one was all elements are composed of tiny indivisible particles called atoms. Atoms of the same element are identical, and the atoms of any one element are different from those of any other element, which this part we still know to be true. Almost. Atoms of different elements can physically mix together or can chemically combine in simple whole number ratios to form compounds. Now that whole number ratios is very important, and we will get very deep into that later this semester. But because he thought that atoms were indivisible, up here, part 1, he says they're indivisible. They cannot be split in half, so they have to combine in whole number ratios. And finally, chemical reactions occur when atoms are rearranged so that atoms are attached in a different arrangement. Atoms of one element, however, are never changed into atoms of another element as a result of a chemical reaction, which is true, as far as we know. The only part of Dalton's theory that was not true was that atoms are in fact divisible. You can divide them into electrons, protons, and neutrons. Electrons were the first subatomic particle to be discovered by J.J. Thomson. He discovered the electron using a cathode ray tube. So this is a tube that has no air in it. It's vacuumed out, and he was able to put a metal disc on one end that was negatively charged, so the cathode, and then a positively charged disk on this end, and he hooked them together with high voltage and actually observed tiny negative particles traveling from the cathode through the vacuum to the anode. And that is how the electron was discovered. So it is a very small, negatively charged particle. There's going to be a table on the next slide that you can copy down all of these little facts about electrons, protons, neutrons. Protons were next. Eugene Goldstein observed a cathode ray tube and found rays traveling in the direction opposite of that of the cathode rays, and so he discovered the proton in much the same way the electron was discovered. And finally, neutrons were discovered by James Chadwick, and he found the final subatomic particle, the neutron. Okay. So here's that table I was telling you about. Here's what you need to know about the subatomic particles. Electrons have a charge of -1, and their relative mass, so their mass compared to a proton, is 1 over 1840. Very, very small. And its actual mass in grams is 19.11 times 10 to the -28 grams. So you can think of the mass of an electron as 0. And we'll measure atomic mass going forward using AMU, or the relative mass. Protons have a charge of +1 and a relative mass of 1. Its actual mass is the same as a neutron, 1.67 times 10 to the -24 grams. Now a neutron has no charge, but its mass is also 1. So it is the same mass as a proton, but it does not have a positive charge. Once all of these subatomic particles were discovered, scientists then needed to think about how were they arranged inside the atom, because they couldn't see inside the atom to see how they were arranged. And this led way to many models of the atom, and these models evolved over time. Models are a great way for scientists to share their ideas with other scientists, and we're going to look at the evolution of the atomic model on this next slide. Okay, so we already talked about John Dalton, and there's his model. I guess it's kind of hard to see. Let me color it in for you. It is just a large gray circle. There we go. That's a little easier to see. Because remember, he thought of atoms as tiny, indestructible particles. So this was the model of the atom before subatomic particles were discovered. Then J.J. Thomson, he discovered the electron, and he pictured electrons as embedded in a sphere of positive electrical charge. It's sometimes called the plum pudding model. So the yellow you can think of as just a positive blob, and the electrons he discovered, he imagined them just sitting in the blob. Okay, and then Ernest Rutherford, his model had a nucleus that was small, dense, and positively charged. The big thing that Rutherford discovered about the atomic structure was that there was a lot of empty space inside of the atom. So he actually was shooting protons through a gold foil, so a very thin piece of gold, and he was expecting a lot of them, because he was going off of J.J. Thomson's plum pudding model, he was expecting a lot of them to bounce off But what he found is the majority of the protons he shot at the gold foil went through. He had a proton detector on the other side. And that proved to him that there was empty space. So let me just draw a little picture. So he had a proton detector over here. And then here's his very thin piece of gold foil. And over here, he was shooting protons at it. And he found a majority of the protons were actually being detected over here. He had another detector up here, and very few of them, I'll just draw less, actually bounced off of the gold foil. So that proved that there's a lot of empty space inside the atom. And an analogy I've heard about how much empty space there is if you went to a professional football stadium, the nucleus would actually be the size of a basketball in the middle of the stadium, and the rest of the atom is empty. So that's how much empty space there actually is in an atom. Then Niels Bohr discovered that the electrons that are outside the nucleus actually move in a circular orbit around the nucleus. And the electrons can jump from one orbit to another when an electron absorbs or releases energy. So a pretty good picture of that would be, let's see, you can actually observe this when it releases light. It's a really common form of energy that electrons release when they move orbitals. So here's our nucleus. And here are some very rough models of orbitals. And let's say we have a proton right here. Maybe this is a hydrogen atom. It has just one electron. If the electron absorbs some sort of energy, this electron can actually jump up briefly to a higher orbital. And then when it moves back down, it has to release the same amount of energy that it absorbed. And finally, Erwin Schrödinger developed some mathematical equations. This model looks kind of messy compared to the other ones, and that's exactly what he meant it to look like, because he was saying that there's no way to predict where these electrons will be, and there's no way to say that they move in an exactly perfect circular motion. They probably more likely move in a specific area or volume, but they move more sporadically than in a circular motion. So he developed mathematical equations to describe the motion of electrons and atoms, and it led to the quantum mechanical model. I'm not sure that we're going to get as far as quantum mechanics in this chemistry class, but if you are interested in it, there are plenty of classes in college that you can take to study quantum mechanics in further depth.